Well, let's pray and we'll get started. Heavenly Father, thank you for today. Thank you for these men and women who are here and the opportunity to come and to study about your hand in creation. The Word says that the heavens declare the glory of our God. Father, I pray that would be true for us, that as we study these things, we would just be in awe of you, of your creativity, of your power, of your wisdom, of your mind, and of your goodness to do all of this. May we know something of your glory because of our studies here in this class. Help us to pay attention well and to learn well, to recall the things that we learn. Father, help me to be clear as I ought to and to lift you up. We pray this in Jesus' name. Amen. All right. So we started last class and talked about a bunch of stuff pretty fast. But I did think, okay, out of that, there are probably two things hopefully we're going to recall that we need to have from now to the end of time. The first one is, what determines a star's characteristic? What one attribute, factor of a star really determines everything? That answer is mass. When we say mass, we mean how much matter, how much stuff, protons, neutrons, electrons, hydrogen, helium, lithium, beryllium, all that kind of stuff, right? So the answer to this is mass. That'll be a question on a test, okay? Guaranteed. The next question is, well, what is a star? How would you define a star?
Gas and plasma.
Okay, it's made of gas and plasma. We're about halfway there. We need to go a little bit further. Because I can have gas and plasma and still not have a star.
And fusion.
It's got to be doing fusion. Okay? We're going to take it one step further. I've got to be doing fusion. It's basically a big ball of gas that's doing fusion in its core. Okay? If it's not doing fusion in its core, it's not a star. Talked a little bit about our star. We said on the scale of all stars, right? Really big, over to really small. Our star is very mediocre. Right about in the middle. We're in what we call an M-class star. We're a very average star. We're about average in terms of brightness. We're about average in terms of color. Our star is the things that are happening with our star, it's a very good example, a very good model of what's happening in all stars everywhere. Okay? So today we will kick off learning about our star. The things that are going to be true of our star are true of not every star that's in existence, but every main sequence star. And that's reflected here. What's happening inside of a main sequence star? And right now you should be asking,
What's happening inside of the main sequence?
you could, but you might just go, hey, what is a main sequence star, right? What does that mean? So let me just talk about that for a
It's
minute.
fusion now.
Huh?
It's doing its fusion now.
Well, that's true. I'm going to kind of take a sidestep for just a minute. All right. You will know all about the main sequence by the time we're done. You'll be sick of hearing it. You'll be able to draw it. You'll have it memorized. You'll be able to tell me colors, relative luminosities, relative brightness, relative temperature, relative mass, everything. You'll have it memorized. It's not that hard, by the way. But you'll have it all. It'll be done. It'll be great. But the main sequence. our star is a main sequence star. Most stars are main sequence stars. Most stars spend most of their life on what we call the main sequence. Okay? There's a reason it's called main. All right? If I were to have a graph of stars and go, okay, I want to put any star that's doing fusion in its core of hydrogen into helium, and maybe we ought to say that, right? So main sequence, these are stars that are doing hydrogen to helium fusion in their core. Okay. Every star's got to be doing this at some point or it's not a star, right? If it has a lot of mass, it looks like it's going to be a star, but it never ignites hydrogen into helium in its core, it's not a star. When it stops doing hydrogen into helium in its core, every star that would possibly be on this graph, this chart, is fusing hydrogen into helium in its core. Okay? Our star is a very mediocre star, right? Very middle. So where are we going to be?
Middle.
In the middle. This says, I don't need you to know, you don't need to have this memorized. You don't need to draw this. You can if you want to. Later on you'll know this, but that's not the point of today, okay? As I use this term, I want you to understand what we're talking about, okay? So here we are, here's the sun, right? Literally in the middle. There should be about half as many stars that we're going to draw that are going to be bigger, and about half as many that are going to be smaller, right? Okay? And so we'll do that. The main sequence kind of does this. Kind of forms a line. Over here you've got really, really huge stars. So over here we're going to have
Small stars.
itty bitty stars. These are going to be red dwarfs. Tiny. Red. What color are we? Yellow. So itty bitty and red, medium and yellow. What's this going to be? Big and blue. Yeah. You get it, right? Okay. And everything in here, what size it is, how bright it is, what has to do with what? One thing. Mass. This is so big because it's so massive. This is so blue because it's so massive. This is so bright because it's so massive. This is so red, so small, so dim, because it's not very massive. Fair enough? It's also not nearly as hot. I wouldn't want to touch it. It's still crazy hot, but it's not nearly as hot as that. Okay? The one characteristic these stars all have is they're fusing hydrogen into helium in their core. Now, they don't all stay here. They all have to be here. Most of their life is spent here. It's like 90% of their life is spent on the main sequence. But when they stop fusing hydrogen into helium in their core, they leave the main sequence. And they get big. I mean, big, big. Our sun, right now, very, very medium. But one day, we would expect it to get very, very large. It's not going to be, when we say the main sequence, I don't mean like, oh, this whole graph is the main sequence. The main sequence is this line, okay? The graph is called the HR diagram, the Hertzsprung-Russell diagram. You don't need to know that. But the main sequence is this line right here, okay? I'm just going to kind of keep drawing it, and I'm going to label it main sequence. Every star that has ever been, while it's fusing hydrogen into helium, lies somewhere on this line. When we say it leaves the main sequence, what we mean is that star is no longer on this line. So our sun one day will not be here. One day our sun will be over here. We'll form a red giant. Okay? We're going to be a whole lot bigger. We're going to be really bright, but we're not going to be that hot. And that will be because we stop fusing hydrogen into helium in the core. Anyway, it's more information than I need you to know right now. As I talk about main sequence, please know I'm talking about this line. That for 90% of its life, every star can be charted somewhere. And by the way, they don't switch places on this line. It's not like, oh, our sun is going to burn all its fuel up and it'll get smaller and so it'll go from here to here. That does not happen. And it's not going to collect more mass and get hotter, and that doesn't happen. Okay, wherever they're at, that's where they're at for 90% of their lives. When they move, they change, they whatever, they'll leave the line entirely and they'll go to some other spot on the graph. Okay, so what is happening inside of a main sequence star? You've just heard it over and over and over again. If you knew nothing else, you must say the one thing they're doing is what? Fusion of hydrogen into helium. We'll learn about that in the next two classes. We're not going to cover it today. And this is where the energy that comes from the sun comes from. This is where the light that comes from our sun comes from. That's where the heat comes from, because it's doing this. This is what makes a star a star. All right, let's dig in. So today, remember, is all about what is happening inside of a main sequence star. So, here we go. What's our sun made of? Gas. What gases? Hydrogen and helium, for sure, right? Anything else? Pardon me. Should we turn off? Might. Okay. Hydrogen and helium for sure. Okay, that's what makes it what it is. Inevitably, you're familiar with the periodic table of elements, right? Okay. Inevitably, there are going to be some of these other elements, but they're not being made in our sun. So if we find them, where did they come from? Well, theoretically, they came from some other star, some other sun. Whatever means God used to get them there, they weren't made in our sun. Our sun is not hot enough to fuse something like hydrogen. It's hot enough to fuse helium, and that's it. I have to go through a lot of changes to make anything bigger than helium, right? So, where is this happening in our sun?
Core.
It's happening in the core. So let's look at this. Let me draw some layers, okay? I've got a core. I've got this. And I've got this. We'll start there. This is our core. Okay. And inside of our core, this is where fusion is happening. I'm going to use a different color to help out for this. This you got to know. There will be a diagram. You're going to have to label it. Okay. So in our core, we've got fusion. The next layer this is referred to as the radiative zone. The next layer does this. Let's see if I can get this right. I'm not going to do it the whole way because it will take way too long and be way too tedious. You're not going to want to do that. This is called the convective zone. Draw that, and then we'll talk about it. What does it mean to radiate?
Cells that die, or no, wait, no, that ain't right.
You're thinking like radiation, killing cells with radiotomy therapy and cancer and stuff?
Yeah.
Not quite. Although the word radiation's in there, right? What does it mean to radiate something?
Give off.
Pardon?
Give off.
To give off. That's simply it. It comes from a source and it's going out. And it's going out. When we talk about radiation, like kind of the core of what you're thinking about with a radioactive element. Well, it has something and it's shooting it off. Could be shooting off an alpha particle. So basically the nucleus of a heliatom. Could be shooting off a beta particle. Could be shooting off a gamma ray. But it's something that was in and it's shot off. So where that matters here is we're taking energy and it's simply passing through. Okay? This material is getting heated here. Gas is getting heated because it's right near the core where this fusion's happening. The sun is not on fire. Okay? This is not a fire. Fire, it's not a good, I mean, it's the best we've got like, on Earth, but it's not good. A good comparison. Fusion is something so much more. In fusion, we're literally converting mass into energy. I mean, we're doing like Einstein equals MC squared type stuff, okay? Converting mass into energy, and that energy is in turn heating up the gases around this. Well, these gases are simply flowing out. The energy from the core is passing right through this radiative zone, okay? But convection is a different matter. In convection, let's say this is a source of heat, okay? And this is a gas. The source of heat heats the gas rises. But as it rises and it transfers energy to the next layer, the gas cools back down, and now it falls down due to density. So that's what's happening in our convective zone. Humor me, okay? Hold up your hands. Come on. I'm just going to wait on you. Do fingers. Fingers are good. Okay. So this is our heat source down here. We get hot. What do? We rise. And we give off our energy and we fall. And we rise and we fall. It's got a little, this is like a little bit of like a Karate Kid type stuff or something, right? So that is convection. Something heats up and it rises. It's just density, right? Warm air rises. It gives off, it transfers its energy, and then it falls back down. Yes? No? Oh, all right, whatever. If you don't care, why do I care? I don't know. So that's what's happening here with convection. It rises, it gives off its energy, it falls back down. Matter's not leaving this shell or this area, okay? This layer. So far we've got 3 layers. We've got a core where fusion's happening. This is the source. This is the engine that drives the nuclear power plant, which is our sun. Okay? It gives off energy with light, with heat, and in the radiative zone, that energy is passing through. In the convective zone, it's rising up. It is transferring, but now the material is falling back down. Okay? Over and over and over again. All right. So those are our first 3 layers. Now, after that, after our convective zone, we've got chromosphere. Let me make sure that I'm not missing anything that you're going to need here. to this, we have a layer that we call the chromosphere. It'll draw it pretty thick in terms of just dark. It's going to be our chromosphere, or I'm sorry, our photosphere. Oh, we got the markers. No, I don't have them. Our next layer is going to be our chromosphere. And then the last layer is going to be our corona. Put these in the right order for you. So we have core, we have radiative zone, we have convective zone, photosphere, chromosphere, and then the corona. Let's talk about some Greek prefixes here. Word photo, do you know what it means?
It's like lights.
It means light. This is the light sphere. Chromo,
Time?
not time, that's chrona,
Yeah, okay,
this
yes.
is with an M, means color.
Oh,
Corona
it's like crowns?
means crown. Okay. Each of these has a name based off of either what it does or what it looks like. So the core is the core because it's in the core. It's the center of this thing. It's pretty dense. This is where we're wildly hot. We're doing our fusion. This is this is the engine that drives everything. Radiative because the energy and matter is simply passing through. It's radiating out. Convective because it's doing the convection cycle thing. Photosphere because this, at least generally speaking, is the first layer we can see. We can't see normally, with normal instrumentation, we cannot see anything below the photosphere. Things are too dense, we can't penetrate it, okay? So this is the light that you see coming from the sun, you're looking at that, okay? Chromosphere is called the chromosphere because it has color. In particular, it has the color red. You don't look at our star and see red normally, right? But when you look at it during a full eclipse, especially an annular eclipse, there are two things that just our position from the moon and the sun is such that the moon, when its shadow passes perfectly in front here, it covers everything except for the chromosphere and the corona. And all of a sudden you see this very, very bright, very, very red ring. It's not big, but it's very bright and it's very red. You can't see it the rest of the time because the light from the photosphere is far too much. But you can see it during an eclipse. And so it's a distinct layer with its own characteristics, and it's called the chromosphere. And finally, this outer layer called the corona, or the crown, okay? And at times, it's relatively close. At other times, it thrusts out quite a ways into space. In fact, oftentimes we are viewed as being in the corona of our sun. You don't think of yourself as being in the sun, right? But this outer layer extends out millions and millions of miles, shooting all these particles out, right? You've heard of solar winds? Yeah, that's coming from the corona. Northern lights. Heard that? Okay. That's because the solar winds, when they come into contact with our atmosphere at the poles, the energy that they have causes oxygen and other elements in our atmosphere to kick off electrons at various wavelengths of light, and it's just absolutely beautiful. Well, but much of this because we're technically considered to be in the corona. It extends out far further than you would imagine, but it's not one consistent shape, right? This looks like some hippie's drawing of the sun or something, but what questions do you have right now? No? Okay. Why is it doing this? Why is this happening? Why is there fusion? Did learn this. It's up on the board right now.
Hydrogen's and helium?
That's what fusion's doing. Why is it doing it? It's up on the board.
Because that's mass?
Because of the mass. Okay, because of gravity. It's a good time to point out, when you look at our star, you don't see it like shrinking and growing, do you? It is, but the changes are so small you don't notice it. There are two forces at work at all times in every, you must know this, okay? This is, you with me? Get this down, you must know this. There are two forces at work at all times in every star, okay? One force is pushing in, and the other force is pushing out. What force is pushing in? Wanting it to shrink. Gravity. Why does it have gravity? How much gravity does it have? It comes from its mass, right? So this is gravity. So gravity is always pushing a star in. Always. And yet our star is not collapsing. It has a tendency to, but it's not doing it. There's another force pushing it out. You don't know the name of it, but you know it's causing it. Just take a look at your drawings. What is it?
Energy of the core is pushing out.
Yeah. Right. So this is from fusion. Energy from fusion. There's a force that's pushing a star out. And gravity is always pushing it in. But a main sequence star is in equilibrium. It's not, I mean, it does this a little tiny bit, but nothing that's noticeable. It's not going like, you know. But later on, it'll do that. When a star stops doing fusion in its core, well, guess what? There's no more energy of fusion. So that star doesn't have any force pushing it out. What's it going to do? It's going to shrink. When it shrinks, what is it going to do? Do me a favor, everybody right now, take your hands. Nice and easy, right here, ready? Take your hands and just squeeze them together. And when you get here, keep squeezing. Squeeze as hard as you can. Hold it for as long as you can. Do you know if I had a thermometer, like one of those like digital things where I could just scan, like your hands would be doing what?
Heating up.
They'd be heating up. Okay? Because you're squeezing them together, right? The same thing's happening in a star. Because of gravity, everything's being squeezed together, and as it squeezes together, it heats up. And so that's what drives fusion. Fusion happens because of mass, because of gravity, because it's being squeezed together, and as it does, it heats up. And when it heats up, it creates an energy of fusion, ultimately, that pushes it back, okay? So, why are we talking about all that? Because we're talking about our sun. It's got mass. It's got sufficient mass that the gravity is enough that it has become squeezed together enough that it ignited in fusion. There are stars that are not quite stars. There's a lot of mass. They get hot, but they don't get hot enough for fusion to ever take off. We call those brown dwarfs. Okay? You don't need to know that right now. I'm just letting you know that that is a thing. Okay? The more mass, the more, say gravity. Gravity. The more gravity, the hotter a star is. The hotter it's gonna burn. The hotter it's gonna burn, the more it's gonna push out, right? But since it was already so massive anyways, it's just gonna be a bigger star. You remember that diagram that we had earlier, right? We had the sun in the middle, a very, very medium star. Something with much less mass, it means it's gonna have much less gravity, which means it's gonna have much less heat. So this end of things, these must have been cooler stars, right? Conversely, if it was a really big star, lots of mass, lots of gravity, lots of heat, these must have been very hot stars. All right. So, I'm telling you, everything in a star comes back to this. Ours, very medium. It's got enough, heats up due to gravity, we get fusion. Fusion creates radiation, creates convection. Energy is getting transferred. We've got first our photosphere, right? We can't see past that with normal instrumentation. In fact, and it's so bright that most of the time it's very difficult to see the chromosphere or the corona. When will I see the chromosphere?
Eclipse.
In an eclipse. Yep. When will I see the corona normally?
All the time.
During an eclipse, right? What were you going to say, Rick?
The corona?
Yeah.
We see it all the time, don't we?
Well, kind of, but it's hard. You don't see these flares and stuff, right?
Oh,
Because of how bright the photosphere is. Okay, so but when that photosphere is blocked, then you can actually see the distinct. You can see whirls and loops that this thing is doing, and it's definitely doing it all the time. All right. Do you feel good about this? Okay. You got to be able to draw that. All right, and you got to be able to play it, label it. You got to know what these things are. Odds are I will probably give you the diagram and I'll tell you to label it. Okay? You might do well to find some way of memorizing these in the right order. Odds are I will probably ask you questions about individual ones. I'll probably say, hey, where is fusion happening in the main sequence star? And you're going to say? Core. I'm going to say, what's the innermost layer of the Earth or the star of a star that you can see? And you'll say? Photosphere. I'll say, which one's red? And you'll say? Chromosphere. I'll say, which one's the outermost layer? And you'll say? Corona. I'll say, where do solar winds come from? And you'll say? Corona. Good. Okay. I'll say, hey, why is the star hot? And you'll say? Fusion. That's good. Or gravity or mass. Yeah. And you need to know this also. You will, because I'll ask short answer questions, you're going to give answers that I wasn't expecting. And I will give you, if you're there, I'm going to give it to you. Okay? I'm not looking for exactly what I was thinking. I'm in the business of giving points, not taking them away. Okay? All right. let's do this. There's another chart, a graph I want you to have memorized. Okay? Just means you gotta practice it. You're gonna have to be able to label it, I'll put it that way. I'm gonna erase this. Kabish. What are the two forces at work in every star?
Gravity.
Gravity and?
The
Mass.
fusion.
Gravity and?
The fusion.
Fusion, right? Which one's pushing a star in?
Gravity.
Gravity. Which one pushes out?
Fusion.
Okay. By the way, what happens if I have no more force pushing out, but I've got a huge mass? What's it going to do?
Collapse.
Compress how far? Depends on how much mass it is, right? What are my options? What's the ultimate
Supernova.
after supernova?
White dwarf.
No, that's little stuff.
Oh,
If it was a huge star, what's it going to become?
A black.
Black hole. Because it's so massive that nothing can, at the end, nothing can stop its contraction in. You get a black hole. All right, so here's your chart. You're going to want to copy this. Get as close as you can on that. I'm going to give you this drawing. I am not going to label your axes for you. I'm going to make you label your axes. I'm going to give you that drawing, and I'm going to ask you to label the axes, and I'm going to ask you to label the layers. Okay? So this point right here is the photosphere. This point right here is the chromosphere. This is what we call a transition region. And up here is the corona. Okay. So what do you see? What do you observe? Tell me about my axes. Which one's my x-axis? Temperature, distance. Distance is my x, okay? Temperature is my y. So what's happening with my x-axis here? Distance is increasing, which fits. These are my layers, right? Photosphere, chromosphere, corona, those are in the right order, going away from the sun. So there's a number of reasons to point that out. One is just if you know the layers of the sun, then you actually kind of already know, okay, these are getting further away. So you know, okay, photosphere, chromosphere, corona, somewhere in there. The only weird thing is this little transition zone. We're getting further away. So if I know that, then there's no reason I should ever label it this way, right? I would know that was wrong, okay? So keep that in mind. That's going to help you. All right, so I'm going further away from the core. I'm in the right order. Photosphere, chromosphere, corona. Okay. What's happening with my temperature? Increasing. Generally speaking.
No, it decreased first.
Generally speaking, as I get further away from the core, what's happening with my temperatures?
Decrease.
Or, well, if they were generally decreasing, then I'd expect it to do just this, right? But is that what you see? No, generally what you see is this. You know, the average trend is we're getting hotter as we get away from. In fact, the further we get, like look at this rapid craziness. It's getting hot fast. And the furthest layer from the sun actually has regions that are the hot, or the furthest layer from the core has regions that are hotter than the core. And by the way, we don't understand why. Okay? They don't know why, we just know that it does. So this is an interesting thing. I put the core up here, you know, this is the core of our sun is roughly 15 million degrees Kelvin. So 15 times 10 to the 6th power. I realize you don't have this nice chart that I do, but you'll get it, and it's in your book if you want to. By the way, did I talk to you about your book? You just go to Moodle and click it and download it, and it's there. So this is 15 million degrees, roughly, and here we are hotter than that at certain points in our corona. That's unexpected, isn't it? Because our energy source is at the core. But due to the complex structure and the way all this is working, we initially have a cooling off in the photosphere. And this is, remember, the photosphere is the layer that's right in contact with that radiative zone, or I'm sorry, with that conductive zone. And then the chromosphere just looks like it's just a pretty consistent from start to finish, whether I'm at the bottom of the chromosphere, the top of the chromosphere, it's just pretty consistent temperature, and all of a sudden we rise rapidly when we get to the corona, which is unexpected. This thing's like flying out millions of miles in space, but it's wildly hot. So this is not what you'd expect, right? I would expect this, but it's not what we've got. Okay, what time is it? I've got time.
1:17.
1:17. All right. Let me just think before So I taught this exact same class last semester, and I taught some things to them that I don't intend to teach to you. I found that it wasn't necessary, it wasn't helpful, okay? It was just more stuff to know. I don't think you just need more stuff to know. So I'm kind of at this point of this chapter, it's like, we're right at the edge of this, okay. I'm not going to throw a bunch of numbers at you, okay? I think I do probably want you to know this number. The core is 15 million degrees, okay? That might be a thing. I might have you label that or ask you that, okay? Again, not a whole bunch of numbers. I don't want you doing a bunch of math. But just I'll let you know for sure if I'm going to want you to know that. But have it in mind, okay? What makes the sun a star?
Having light of its own.
Pardon?
Having light of its own.
No. No. Why is it a star?
Fusion.
It's doing fusion in the core. That's it. Why is it doing fusion in the core?
Because of gravity.
Okay, why does it have gravity?
Because of that.
Because it has mass. So you got a lot of mass in one little space, and gravity is the force that drives it in, and as it drives in, it gets very
Condense.
hot.
Oh, okay.
How hot it gets is directly proportional to how massive it is. Directly proportional. If you had little hands and you were squeezing, your hands wouldn't get that hot, right? But if you had big old massive monster hands and you were squeezing, they'd get very hot. And I realize that's an imperfect analogy, but the more mass you have, the hotter it's going to get. The more mass, the more heat. Okay? If you have a lot of mass but not enough mass, you won't cross the threshold to ever have fusion ignite in the core. And you'll be a brown dwarf. Very, very faint. It'll produce a little tiny bit of light. That's why I kind of went, that's not... Brown dwarfs produce a little tiny bit of light. But, you know, then again, I'm producing light. Like, you could use an infrared camera on me and I'm producing light. Yeah, but, you know, you're not going to confuse me with a star, right? So it's got to have enough mass that it has enough gravity that it gets hot enough that fusion begins. And then everything else will flow through. Because now, as much as I've got gravity pushing in, I have this other force pushing out. The star is going to come into equilibrium, it's going to come into balance. We're going to have these layers. What's my first layer at the center? Core. What must you know about the core? It's where fusion happens and what temperature? 15 million. Okay? I want you to know that number. I'm just telling you now. Okay? Next layer after the core? Radiative zone. Okay? Things are simply radiating out. If this were high school, I would totally I'd have like a sun dance for you or something. Kevin knows them. I made you guys learn gangster science, right? Prophase, metaphase, anaphase, telophase. Yeah, we would definitely have a dance. You'd have like the core, and then you'd like radiate, and then you'd have convection. I don't know. You need to do something though. You got to know. You've got to know. Don't make fun of him because he had to learn gangster science. You've got to know that it's radiative and then convective, and then we have the photosphere, right? The light. It's the first one. An easy thing to remember that by is it's the first one we can see. Right? The photosphere. It's where our light comes from. By the way, it also happens to be not that warm. Okay. Then chromosphere. Why is it called a chromosphere? Color. What color is it? Red. When can you see it? During an eclipse. Good. And then we have the corona. What's the hottest layer of the sun? Corona. That is counterintuitive. Completely counterintuitive. What's the thickest layer of the sun? Corona. It's not the densest, but it is the thick. I mean, just in terms of where it starts and where it ends, it goes and goes and goes. Okay? All right. You got any questions for me? And I will see you next week. God bless. I show you all my stuff.
Wasn't Dunny in his class too?
No.
No? Who's sitting next to you the other day?
Yeah, half Daniel was with me.
In math, that I know.
Yeah.
But I thought you were with someone.
No, nobody just took it.
Are you last year?
Yeah.
I was actually going to ask you the
What's
same
up?
thing about that.
Everything figured out?
Did you understand everything?
No, that's fine, that's fine. I think you can go right now, try to download the test.
That's just not the stuff I'm a science person. Big science person. Yeah, it makes it easy.
Very strange. Okay. Help at, is it help at Jacksonville College or something like that? Give me 1 second, I'll find it.
So, need help?
Yeah, I was gonna ask you, can I meet up with you a little bit later?
Yeah, of course.
Like maybe 4?
Let me know.
Okay, thank you.
Can you go to your JAG mail or what it's called?
I ain't gonna lie, I've never went on that before. I'm a new student.
Okay. Is this your first semester?
Yes, sir.
Okay. Y'all want to just walk with me? 'Cause I don't have the answer. Do you have time for that?
Yes, sir.
Okay, well, let's go to, take a walk and get an answer. I gotta shut this down.
Is it gonna take like more than like, is it gonna take a minute? Cause I gotta practice that too.